Hello students, in this section we will solve linear inequalities. First, let's discuss inequalities. They are algebraic expressions related by the following: is less than. For example, we might say that 2 is less than 3. Is greater than, this is the is greater than symbol, in which case we might turn the previous statement around and write 3 is greater than 2. Is less than or equal to. There we might say that 5 is less than or equal to 7. We might also say that 7 is less than or equal to 7. When we use the less than or equal to, one or the other of those symbols will be correct. In our first case, the less than symbol is true, and in the second case, the equal to part is true. And lastly, is greater than or equal to. For example, we might say that -2 is greater than or equal to -10, and this gets a little bit tricky, but -2 sits to the right of -10 on a number line, and therefore we say that -2 is greater than the -10. And again, it's the greater than symbol that's the correct part here, or the true part. In example 1, we will write each inequality in interval notation and graph the interval on a number line. So we have the inequality, all numbers x that are greater than 3. If we think about a number line, graph first, I want you to locate 0, and then locate 3, which is 3 units to the right of 0. And then these numbers that are greater than 3 are to the right. So we're going to bold that arrow to the right. Notice that we use the parenthesis with the greater than symbol. And in interval notation, we use the same symbols that you'll see in our graphs. Interval notation, we would say the solution set is 3. And then including all these numbers in the positive direction, in the direction toward positive infinity. The parenthesis in both symbols shows that the 3 is not included. And with an infinity symbol, we'll always use a parenthesis. That's a direction and not a stopping place. So we've got our 3 forms of expressing this inequality. We can use the inequality notation, interval notation, or a graph. In part B, we're going to use a betweenness, kind of a 3-part inequality, and describe all values x that are greater than -2 and less than or equal to 4. Beginning with a graph, let's locate -2, and let's locate +4. We're going to include values that are greater than -2, but not including it, therefore use the parenthesis notation, up to and including 4. And the way that we show inclusion of an endpoint is with a bracket. So notice, with the strict inequality, we'll use a parenthesis. With the non-strict inequality, such as a less than or equal to, we're going to use a bracket to show that the endpoint is included. Now, once you can see a graph, then you can just transfer that inequality to interval notation very quickly using the same symbols. We've got this parenthesis at -2, up to, and including 4 with a bracket. All 3 equivalent forms. We're going to solve some inequalities. And solving linear inequalities is similar to solving linear equations. First, let's determine what a linear inequality in one variable is. Well, it can be written in the form ax plus b is less than 0, ax plus b is less than or equal to 0, ax plus b is greater than 0, or ax plus b is greater than or equal to 0. So these all are very linear in nature because they're going to have your variable to the first power. Here a and b are real numbers. We don't actually show a c in there, do we? A and b are real numbers, with a, our coefficient of x, not equal to 0. Because if it were 0, it would cause that x term to disappear and we would no longer have a variable, and this wouldn't be what we would call a linear inequality in one variable. Okay. Examples of linear inequalities: x plus 5 is less than 2, y minus 3 is greater than or equal to 5, and 2k plus 5 is less than or equal to 10. So notice in each case we see a variable to the first power. Now we're going to talk about our methods for solving these inequalities. And I'm going to write an example here. 2 is less than 3. That's a true statement, isn't it? So our addition property of inequality works. We can add the same number to each side without changing the truth of that inequality. For example, if we add 1 to each side of this inequality, then we have another true statement: 3 is less than 4, and that's still true. If we've got the statement 2 is less than 3, and we want to subtract a number from each side, like maybe we subtract 2 from each side of this inequality, well, that gives the statement 0 is less than 1, and that's still true, isn't it? So our addition property of equality still holds. How about the multiplication property of equality? Beginning with, again, the statement 2 is less than 3. Let's say we multiply each side by 5. Times 5 times 5. Well, 2 times 5 is 10, and 3 times 5 is 15, and 10 is less than 15. And it looks like this multiplication property is holding until we do this, okay? If we multiply or divide each side by a negative number, we need to switch the direction of the inequality to maintain a true statement. Watch this. Starting again with 2 is less than 3. Suppose that we multiply each side of this inequality by a negative number like negative 10. Times negative 10 on the left and times negative 10 on the right. 2 times negative 10 is negative 20. 3 times negative 10 is negative 30, and negative 20 is not less than negative 30, it is greater than negative 30. Now I know that sounds a little weird, but negative 20 sits to the right of negative 30 on a number line, so it is greater. So this is what you need to remember about solving linear inequalities. Okay, write this sentence down. If we multiply or divide by a negative number, switch the direction of the inequality. And that's all you need to know about solving linear inequalities. That's the important thing to remember right there. Okay, so let's look at some examples. Here we're going to, in example 2, solve each linear inequality, write the solution set in interval notation, and graph it. In part A. So just think of this as I'm going to solve a linear equation, okay? So let's use our addition property of equality, and let's subtract 7x from each side. 8x minus 7x is 1x. Next, let's add 1 to each side. 2 plus 1 is 3. X is less than 3. There's our solution in inequality form. I'm going to graph this. So find 3 on your number line, and we want to include all numbers less than, not equal to, less than 3. So numbers like 2 and 1 and 0 and negative 1 are all solutions, okay? There are many, infinitely many solutions to an inequality. We can describe them with a graph. In interval form, we would say this solution set includes all numbers from negative infinity to 3, 3 not included, and we never include an infinity symbol, whether positive or negative, because it's not a stopping place, it's a direction, okay? And this arrow of our graph is going in the direction toward negative infinity. In part B, negative 2r is greater than negative 12. Here we're going to divide each side by negative 2. Left and right side. Okay, so when we multiply or divide by a negative number, we must switch the direction of our inequality symbol to maintain a true statement. R is less than 6 is our solution. Let's graph it. Find 0, find 6, and let's identify all numbers less than 6. Okay, and we do that by simply shading the points for all of these numbers to the left of, which is less than 6, parenthesis, because this is a strict inequality, and in interval notation, we would write negative infinity to 6, because this arrow goes in the direction of negative infinity. Part C, here we're going to multiply each side by 2. Now, we do not have to switch the direction because we're multiplying each side by a positive number, aren't we? Half times 2 is 1. We're multiplying reciprocals there. So 1x is less than or equal to negative 12. As we graph, it's going to come a distance to the left of 0. And let's call this negative 12. We're going to graph all numbers less than or equal to. Less than or equal to. Bracket because of the equal to part. And less than are all of these values to the left toward or in the direction of negative infinity. In interval form, negative infinity to negative 12. Now, when you are writing your interval notation form of these solutions, we'll always put the smaller value, or in this case, direction on the left, with the larger value on the right. Always. Okay, smaller on the left, larger on the right. That's something that's very important to remember as you're writing interval notation. Continuing with part D, let's combine our like terms on the left and write 4x plus 2 is less than 7x minus 5. Next, I'm going to subtract 7x from each side. 4x minus 7x is negative 3x. The same step, I'm going to subtract 2. Negative 5 minus 2 is negative 7. Now to isolate x, we've got to divide each side by negative 3. Careful here, okay? As we divide each side by a negative quantity, we need to do what? We need to switch the direction of the inequality symbol. So our less than becomes a greater than. It's the only new thing, really, that you've got to remember about this section. Solution, all x greater than 7/3. Now, 7/3 as a mixed number, 3 divides into 7 twice with 1 left over. So 7/3 is the same as 2 and 1/3. So as we think about a graph, locate 0, okay, and this space between 2 and 3, let's divide into thirds. Okay, so 2 and 1/3 is 2 and 1 of those thirds. Now we want to describe numbers greater than 2 and 1/3. So parenthesis and arrow to the right. Okay, these larger numbers are to the right on the number line. In interval notation, I'm going to use the improper fraction 7/3 to positive infinity. And lastly here for part E, let's Simplify each side. Start with your distributive property. 4x minus 4 minus 3x is greater than or equal to negative 15 minus 2x minus 1. Combining like terms on the left, x minus 4. And combining the negative 15 and negative 1, let's write that as negative 2x minus 16 on the right. Next, I'd like to add 2x. X plus 2x is 3x. And let's add 4 to each side. Negative 16 plus 4 is negative 12. So as we use our addition property of equality, we don't ever have to change a direction. Okay? And we're not going to have to change the direction of our inequality symbol here either, because we're going to divide each side by positive 3. X is greater than or equal to negative 4. Locate negative 4 on your number line, and greater than or equal to. Okay, shade all the numbers greater than negative 4 and use a bracket to show that we get to also include negative 4 in the solution set. Interval notation, bracket at negative 4 and then off in the direction of positive infinity. Okay, always a parenthesis with an infinity symbol. Next, let's look at an application. Maggie has scores of 98, 86, and 88 on her first 3 tests in algebra. She wants to maintain an average of at least 90, or an A, after her 4th test. So I wonder what score she must have on that test. Well, let's let X represent this 4th test score. And since she wants her average to be at least 90, her average is the typical average here, where we add the values and divide by the number of them. So after that 4th exam, we would add the values 98 plus 86 plus 88 plus X, this score on her 4th test, and divide by the number of tests, which would be 4. Now we want this average to be at least 90, and that means we want the average to be greater than or equal to 90. So we've got our inequality. Now let's solve. Go ahead and add 98 plus 86 plus 88. That's 272. Next, let's eliminate the fraction by multiplying each side by 4. So 272 plus X is greater than or equal to 360. And last, let's subtract 272 from each side. X is greater than or equal to 88. So in order to maintain at least her A, at least an average of 90, she's going to have an 88 on the 4th exam. And I'm going to say at least 88. Okay, and we can substitute 88 for X, add our 4 values, divide by 4, and show that we get 90. If she scores higher than 88, then that average will be higher or greater than the 90. So that's a neat little application. It's something you might actually use later this semester. And our last page here of notes for this video, we're going to look at some 3-part inequalities. Inequalities that say that one number is between 2 other numbers is a 3-part inequality. For example, we can say that 40 is between 29 and 50. So there we would write 40 is greater than 29 and less than 50. So these are betweenness kinds of problems. Now, as we solve 3-part inequalities, when you're presented with them, your variable expression will be in the middle. Notice that's the case with both parts A and B. And we're going to isolate that variable in the middle using our properties of inequality with all three parts. Okay, so in the middle we see 3x minus 1. Let's add 1 to each of these parts and rewrite this inequality as 3 is less than or equal to 3x, which is less than or equal to 9. So do the same thing to all three pieces to keep this balanced. Last, we're going to divide each part by 3. Notice we're dividing by positive 3, so don't worry about switching any directions of things. So that's a 1 is less than or equal to x is less than or equal to 3. As we graph that solution set, okay, we're going to highlight or identify all numbers that are greater than or equal to 1 and less than or equal to 3. Bracket at 1, shade all the numbers in between, then up to and including 3, so bracket at 3. And our interval notation is going to look just like our graph. Same symbols, brackets to show inclusions of the endpoints. Lastly, part B, let's start by subtracting 3 from each piece. Negative 6 minus 3 is negative 9. 3 minus 3 cancels out. And 5 minus 3 is 2. Next step, we're going to multiply each piece by negative 3 over 1, which is the reciprocal of negative 1/3. So negative 3, okay, negative 3 over 1 and negative 3 are the same thing. In the middle, negative 3 over 1 times negative 1/3 a, and on the right, negative 3 times 2. Right, now we're multiplying through by a negative quantity, so we've got to switch the direction of our inequality symbols. Okay, that less than becomes a greater than, and this less than or equal to becomes a greater than or equal to. So what do we have? We've got 27 is greater than a, which is greater than or equal to negative 6. I'm going to rewrite this inequality with our smaller number on the left and the larger on the right. So think about just picking this up, turning it 180, and laying it back down. Negative 6 is less than or equal to a, which is less than 27. So we've got a wedged in between negative 6 and 27. Graph. If this is 0, negative 6 is to the left and positive 27 is to the right. We get to include negative 6, therefore bracket. All these numbers up to but not including 27, therefore use the parenthesis symbol at 27. Interval notation, same symbols, negative 6 with a bracket, up to 27 with the parenthesis. Now you may have learned in the past to use a solid circle to show that an endpoint is included and an open circle to show that it's not. And that's still correct, but it's not going to lead us toward knowing what symbols to use with the interval notation. So I want us to get used to using our brackets and parentheses on our graphs so that we can connect that with our interval notation. All right, students, good luck on these. Keep working hard out there and stay positive.